There are some medical mysteries that feel less like a puzzle and more like a locked room.
Yeah, that's a good way to put it.
Like you can see the problem, you know exactly what's wrong inside the room, but you cannot get through the door to fix it.
Right. Which is basically a surprisingly accurate description of the last 30 years of genetic medicine.
Right. And today, for you listening, we are talking about a disease that has been stuck in that locked room for a really long time. It's called Myotonic Dystrophy Type 1, or DM1.
Mm-hmm.
And the source material we are deep diving into today, this phase 1/2 clinical trial for a drug called del-desiran. It feels like someone finally found a key, or I don't know, maybe a battering ram.
I'd say it's more like a lockpick, a very, very sophisticated molecular lockpick.
But, and there's a huge but in this deep dive, just because you open the door doesn't mean everything goes smoothly.
Oh, absolutely not.
We have a lot to unpack here. We've got a new, almost science fiction style drug technology, some really confusing results where the math doesn't quite seem to add up, and a safety profile that definitely raises some eyebrows.
It's your classic case of early-stage drug development. You have a quote-unquote hero molecule that does something incredible, but it comes with a cost.
Right.
And understanding that trade-off is really the core of what we're trying to do today.
Exactly. So let's start with the stakes. For the listener who might not know, what exactly is myotonic dystrophy type 1? Because I think when people hear muscular dystrophy, they have a very specific image in mind. But DM1 it's different, isn't it?
It is. It's the most common form of adult-onset muscular dystrophy, but just calling it a muscle disease really sells it short.
How so?
Because it's a multi-system disorder. Yes, you have progressive muscle wasting and weakness, but you also have cardiac conduction defects, so heart problems. You have cataracts. You have cognitive issues. It affects the gastrointestinal tract. It really just kind of unravels the body on multiple fronts.
And the prognosis?
It's tough. It causes significant disability, and it shortens life expectancy. And the hardest part, the part that makes this deep dive so urgent, is that right now, the medicine cabinet is empty.
Empty. Like nothing.
Completely empty. There are 0 approved therapies that treat the root cause of DM1. Doctors can manage the symptoms, give you a pacemaker for the heart, maybe braces for the legs, but the disease itself just keeps marching on.
Which brings us to our source material. We are looking at a study on del-desiran, which is being developed to stop that march. But to understand how the drug fights the villain, we have to understand the villain itself.
Right. We have to look at the genetics.
So I was reading about the genetics here, and it mentioned something called a toxic gain of function. Now, usually when I hear about genetic diseases, it's because something is broken or missing.
Like a missing piece of code.
Yeah, exactly. Like you don't have the gene to make insulin, or you're missing a structural beam in the muscle.
Right, that's the traditional loss of function model. DM1 is the exact opposite. You haven't lost anything, you've gained something terrible.
So the gene has just gone rogue.
In a way. It happens in a specific gene called DMPK. Normally, this gene codes for a protein kinase that helps your muscles and heart work properly, but in people with DM1, there is a mutation in the DNA. It's called a trinucleotide repeat expansion.
Repeat expansion.
That sounds like a skipping record.
That is the perfect analogy. Imagine you were typing a sentence, the cat sat on the mat, but the key gets stuck.
Okay.
So you type, the cat sat on the mat at it for hundreds or even thousands of times.
And the cell actually tries to read that gibberish.
It does. It transcribes that DNA into messenger RNA or mRNA. And this is where the toxic part comes in. That mutant mRNA with all those extra repeats, it becomes physically sticky. It clumps together inside the nucleus of the cell.
Okay, so you have these microscopic hairballs of RNA just clogging up the nucleus. Why is that lethal? Does it just take up space?
It's worse than that. Those clumps act like a trap. They bind to other proteins that the cell desperately needs for other jobs. Specifically, they kidnap a family of proteins called muscle-blind-like proteins. Muscle-blind. That's a really vivid name.
It is. These proteins are splicing regulators. You can think of them as the film editors of the cell.
Okay, I like this. Let's ride the film editor analogy.
All right, so your DNA is the raw footage. But to make a functional protein, you need to cut and paste that footage together. That's splicing.
So editing the footage.
Exactly. Depending on how you edit it, you can make an action movie or a drama from the exact same footage. Your body does this constantly. It makes fetal versions of proteins when you're a baby and adult versions when you grow up.
But in DM1, the editors, the muscle-blind proteins, are trapped in those toxic RNA hairballs.
They are held hostage, so the movie goes out unedited, or worse, it's edited wrong. This is the dysregulated alternative splicing, or missplicing. Adult muscles start receiving instructions meant for a fetus.
Wow. And that's what causes the symptoms.
Yes. For example, there's a chloride channel that needs to be spliced correctly for your muscles to relax. In DM1, it gets misspliced. So when you grip a door handle, your hand locks up and you literally cannot let go. That's called myotonia.
That is incredibly specific and terrifying. It's like the instruction manual for the body is being garbled in real time.
It really is. And that's why this drug, del-desiran, is such a massive deal. It's not trying to fix the chloride channel or the heart muscle directly.
It's going to the source.
Right. It's trying to go into the nucleus, find those toxic RNA hairballs, and destroy them.
Search and destroy.
Precisely. If you destroy the toxic RNA, you release the hostages, the muscle-blind proteins, and the editors can go back to work.
Okay, so that's the mission. Let's talk about the weapon. The study calls this drug an antibody-oligonucleotide conjugate, or AOC. That is a mouthful. It sounds like something strictly for the lab coat crowd.
It does, but the concept is actually very elegant. You can break it down into two parts: the vehicle and the passenger.
The vehicle and the passenger. Go on.
The biggest problem with treating muscle diseases is getting the drug inside the muscle. Muscle tissue is dense, it's vast, and it has barriers. You can't just inject generic DNA into the blood and hope it finds its way into the biceps.
So you need a delivery truck.
Right. That's the antibody part of the conjugate. In this case, they engineered an antibody that targets something called transferrin receptor 1.
Why that receptor specifically?
Because muscle cells are absolutely covered in them. The transferrin receptor is like a VIP entrance for iron. Your muscles need a lot of iron to function, so they keep that door unlocked and unguarded.
Sneaky. So the antibody knocks on the door and says, "Hey, I'm just here for the iron delivery."
Basically, it latches onto the receptor and the muscle cell pulls it inside. It acts like a Trojan horse.
And once it's inside,
The Trojan horse opens up and releases the passenger. That's the oligonucleotide. It's a small synthetic strand of genetic material that is specifically designed to match that toxic mat-at-at repeat we talked about earlier.
so it's a guided missile for the typo. The antibody is the guidance system, and the oligonucleotide is the payload.
Exactly. It finds the toxic mRNA, binds to it, and that binding signals the cell's waste disposal system to come over and shred it.
So,
Yeah.
antibody gets you in. Oligonucleotide destroys the sludge, the editors are freed, the movie gets edited correctly, and the patient gets better.
That is the hypothesis. And that brings us to the actual trial.
The moment of truth. This was a phase 1 to 2 trial.
So small scale, right?
Yes. Phase 1 is primarily about safety, but they also want to see if the drug actually does what it says on the tin. It was a multi-center, double-blind, randomized, placebo-controlled trial.
The gold standard.
Exactly. They evaluated the participants at 43 days for the lowest dose and 92 days for the higher doses. The data we're looking at breaks down into 4 main groups. You had a placebo group, 10 people, and then 3 groups getting the drug at different strengths. 6 people got 1 milligram per kilogram, 9 people got 2 milligrams, and 13 people got 4 milligrams.
Making 38 participants total who got an infusion. And we really should pause to appreciate the people in these trials. They are volunteering to have a brand new experimental genetic technology injected into their veins. That takes serious guts. It really does, especially since they also agreed to muscle biopsies. They literally had chunks of muscle removed so the researchers could see if the drug was actually working inside the tissue.
So let's get into the results, because this is where things get, well, weird. I was looking at the data in the source material, and I thought I was reading it backward.
You're talking about the paradox of the dose.
Yeah. Okay, so usually if I take more medicine, I expect a bigger effect. If 1 aspirin helps a headache, 2 helps more. But here, they measured how much of that toxic mRNA was destroyed. And the lowest dose group, the 1 milligram group, had the best result.
It's highly counterintuitive, isn't it? The 1 milligram group saw a 46% reduction in the toxic RNA.
Which is huge. That's nearly half the sludge gone.
It is. But then look at the highest dose. The 4 milligram group only saw a 37% reduction. The 2 milligram group was at 44%.
And placebo was, what, basically 0?
Placebo actually saw a slight increase of 0.9%, which is basically no change.
So you gave them 4 times as much drug, and it destroyed less of the target. How is that even possible? Did the drug just stop working?
This is one of those moments where biology reminds us that it's not just simple math. The leading theory here is about that VIP entrance we talked about, the transferrin receptor.
The door to the muscle cell.
Right. Imagine a nightclub with one bouncer. If you send 5 people to the door, they all get in quickly. But if you send 500 people all at once...
A crowd crush.
Right.
Bottleneck.
Exactly. You saturate the receptors. The pharmacokinetics showed that the drug concentration in the blood went up proportionally with the dose, but if you flood the system with too much antibody at once, you might jam the doors, or the cell might realize something is weird and actually downregulate the receptor, basically locking the door because there's too much traffic.
So the high dose created a traffic jam on the surface of the cell, so less of the actual medicine got inside to do the job.
That's the theory for why the RNA reduction wasn't linear. But, and here's where it gets even more confusing, we have to look at the second efficacy metric, the pharmacodynamics, the splicing.
Right. The movie editing. Did the editors get back to work?
This is the functional fix, and here, the results completely flipped.
Let me guess. The low-dose group, the ones who cleared the most sludge, did they have the best splicing?
No, they barely improved at all. The 1 milligram group had a 3% improvement in the missplicing score. That's statistically almost nothing.
Wait, they cleared 46% of the toxic RNA, but the splicing didn't get better.
Correct. Placebo actually had a 7% reduction in missplicing, just by chance.
But the high-dose group, the one with the traffic jam.
The 2 milligram and 4 milligram groups showed a 17% and 16% improvement in splicing, respectively.
Okay, my brain is breaking a little bit. The high dose cleared less sludge, but fixed the problem more.
It's a fascinating paradox, and it suggests that maybe total RNA reduction isn't the only thing that matters. It might be about where the drug is going inside the cell.
What do you mean?
Muscle isn't just a bucket of water. It has structure. It has compartments. It's possible that the higher doses, despite the saturation issues at the surface, managed to push the drug deeper into the tissue or into the specific nuclei where the splicing is most critical.
So even if the total numbers look weird, the drug got to the right place in the high-dose groups.
That's the best explanation we have right now. And honestly, for a patient, that's what matters. You don't care about the RNA number on a chart. You care if your muscles work. And the amelioration of missplicing in the high-dose groups proves that the drug is biologically active. It's literally fixing the instruction manual.
So, broadly speaking, the headline should be popping champagne corks. Functional correction achieved. The splicing is fixed.
Scientifically, yes. It is a massive proof of concept. It proves you can target a specific gene in human muscle and fix a molecular defect. That is historic.
I feel the heavy atmosphere entering the room. We have to talk about the cost of doing business.
Yes, we do.
And I don't mean the price tag. I mean what happened to the participants. Because this safety report, it's not exactly clean.
No, it's not. And we need to be very transparent about this. Safety is the primary endpoint of a phase 1 trial. If the drug works but it hurts you, it's not a viable medicine.
The report says mild or moderate adverse events occurred in 35 of the 38 participants who received an infusion.
Now let's contextualize that first number. In infusion trials, mild events are incredibly common. You get a headache, you get tired, maybe the spot on your arm where the needle went in gets red. That 35 out of 38 number sounds scary to a layperson, but it's often par for the course in early studies.
Okay, fair enough. But we aren't just talking about headaches.
No, we are talking about the severe, serious adverse events.
Well, there were 2 of them.
2 participants experienced reactions severe enough to be classified as serious. And crucially, these happened in the 2 milligram and 4 milligram groups.
The groups that actually saw the functional benefit?
Exactly. The groups that got the functional fix also carried the highest risk. One of these participants even had to discontinue the trial entirely.
So 2 people out of the 22 people in those higher dose groups. That's a real risk.
It is significant.
So if you're a patient listening to this, you're probably feeling really conflicted right now. The low dose is safe, but it doesn't seem to fix the splicing. The high dose fixes the splicing, but you have a real chance of a serious medical crisis.
That is the dilemma. It's what we call a narrow therapeutic window.
Threading the needle.
Exactly. You have to find a dose that is high enough to work, but low enough to be safe. And right now, based on this phase 1-2 data, that window looks very, very small, maybe even closed with this specific formulation.
But we also have to weigh the alternative, and this is the part that's really hard to quantify. DM1 isn't a headache. It's a progressive, devastating disease.
That's the risk-benefit calculation that regulators face.
Right.
Doing nothing has a 100% rate of adverse events because the disease will get worse. It will disable you. So the FDA and the medical community have to decide. Is this level of risk acceptable to stop a disease that is guaranteed to harm you?
And I guess the hope is that they can tweak the drug, right? This is just version 1.0.
Exactly. This is the first draft. They need to figure out why those reactions happened. Was it the oligonucleotide, the genetic silencer itself, or was it the antibody, the delivery truck?
If it's the truck, you just get a new truck.
Theoretically, yes. If the toxicity is coming from the transferrin antibody triggering an immune response, maybe they can engineer a steadier antibody. Or maybe they just change the dosing schedule, give smaller doses more frequently to avoid that traffic jam at the receptor.
So it's not game over. It's more like back to the drawing board for refinement.
It's definitely not game over. In fact, despite the safety signals, I would argue this is a watershed moment for the field. Because we have crossed the threshold of undruggable. For 30 years, we've looked at DM1 and said, we can't fix RNA in muscle. It's too hard. This trial proves it's not too hard. It's possible.
The mechanism works. The key actually fits the lock.
The key fits. Now we just need to make sure turning the key doesn't set off the burglar alarm.
That is a fantastic way to put it. And before we wrap up, I want to zoom out for a second. We've been hyper-focused on myotonic dystrophy. But this technology, this antibody-oligonucleotide platform,
Yes. The bigger picture.
if you could swap out the payload and you could swap out the address on the delivery truck, this could be huge for other diseases, right?
It's potentially revolutionary. Think about it. We use transferrin to get into muscle. But what if we find an antibody that perfectly targets neurons in the brain or cells in the kidney?
You could attach a different oligonucleotide to target Huntington's disease or ALS.
Theoretically, yes. We are moving away from the era of small molecule drugs, which are basically chemical hammers that just hit everything, toward an era of escorted molecules.
Escorted molecule.
It's personalized, precision mail delivery for genetic errors. If you're listening to this, imagine a time where we can theoretically silence any mutant gene in any tissue, provided we have the right address and the right key.
That is a staggering thought. It feels like we're standing on the edge of a completely new map in medicine.
We are, and like any new map, the edges are dangerous. That's what those adverse events remind us. We are exploring unknown territory. But it's really the only way to find new treatments.
Well, for the families waiting for a DM1 cure, this trial is a mixed bag. But it's a bag that contains real, tangible hope.
I completely agree. It shifts the conversation from, is a cure even possible, to how do we make the cure safe? That is a much better problem to have.
It really is. It's the difference between being lost in the woods and seeing a path, even if that path is steep and rocky.
Well said.
This has been a fascinating look at the messy, difficult, but incredibly hopeful reality of drug development. Thank you for walking us through the data.
It was my absolute pleasure.
And to everyone listening, thank you for joining us on this deep dive. Keep asking questions, keep looking for the answers, and we'll see you next time.